S. Chand presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
So we all know that gaseous molecules are constantly moving. In different directions they are moving with different speeds. So do we think that they all move with the same speed or they move with the different velocities? Welcome to S. Chand Academy. Myself Dr. Mamta Sethi. Today I will be discussing with you the kind of distribution of velocity the gaseous molecules follow while moving. So if you want to read in details about the topic, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. So let us now have a look at the distributions of molecular velocities which the gaseous molecules they follow. Now this distribution, the kind of motion gaseous molecules undergo, was well studied by the scientist Maxwell Boltzmann, and he gave a very famous equation in order to explain the behavior of the gaseous molecules. Now he gave this expression which is known as Maxwell Boltzmann distribution of molecular velocity. So Maxwell Boltzmann distribution equation. According to this equation, what happens that gaseous molecules they move, but they do not move with the same velocities, right? They all are moving with different velocities. Some are moving slow, some are moving fast, some are moving very fast. So the gaseous molecules are there, as we know that in a sample of gases there are many molecules. So out of all these molecules, some may be moving very slow, some may be moving very fast. Now how do we know? Maxwell Boltzmann actually tried to give the quantitative expression as to how many molecules exactly are moving with what velocities, right? So if I am saying that the molecules are moving with lesser velocity, then how many? What is the fraction of these molecules which are moving with lesser velocity, and how many molecules are exactly moving with very high velocity? And most of the molecules would be moving with these velocities, right, which are in between very less and very high velocity. So here I would like to give an analogy. I always prefer to give this example as in a class, 100 students class is there. Out of all these students, some are exceptionally bright and they would be scoring always higher marks. So they can be always compared to the molecules which are having very high velocity. Similarly, only a few will be there who are performing really poor. They can be compared to the molecules which are having very less velocity, but masses, average number of students, most of the students are having scores like average score. You know that in a class बहुत सारे बच्चे ऐसे होते हैं तो स्कोर करते हैं between let's say 40% to 80%, maybe 20% students they score 90% and above, and 20% of the student or maybe lesser than that are only those who fail or they score below average marks. So in the same manner, gaseous molecules also have been divided into different ranges. There are number of molecules. So what distribution do they follow? It is given by this equation. So what is there on the left hand side? It is dN upon N. Suppose there are capital N number of molecules. Now what does dN upon N represents? dN upon N represents the fraction of molecules which are having velocities between the range. When we talk about the fraction, there will always be a range. So the molecules which are having velocities between C and C plus dC. Because I won't be defining it, it's not like एक मॉलिक्यूल जो है वो 200 मीटर पर सेकेंड से मूव करता है and the other molecule is moving with 500. In that way, if I keep on defining the velocity of one molecule, it would not be possible. So therefore, what do? We always define a range. तो एक range define है that molecules, let's say from 200 to 300 meter per second. How many molecules? कितने molecules हैं जो 200 मीटर पर सेकेंड से 300 मीटर पर सेकेंड? कितने मॉलिक्यूल्स हैं जो 900 मीटर पर सेकेंड टू 1000 मीटर पर सेकेंड की स्पीड से मूव करते हैं? सो दिस हैज़ बीन गिवन बाय द Maxwell Boltzmann equation. So this represents the fraction of those molecules which are having speeds between this, and this is given by this factor. Now here we see that it is a combination of two factors. One is your exponential term and another is called as pre-exponential term. So basically if you look at this expression, this part of the expression is what? This is mostly constant. For a molecule, for a fixed molecule, let's say nitrogen molecule के लिए, oxygen molecule के लिए, for carbon dioxide, this will always, mass will be fixed, pi is fixed, 2 is fixed, R, which is gas constant at a particular temperature and pressure, temperature is always fixed. So this is kind of fixed or constant quantity. So what is the variable here? So it is c square and this exponential term. Now when we plot this distribution with dn upon n on y-axis versus speed, so we see here that the two contributing factor which decides the nature of this curve are this square factor and exponential factor. Now we all know that, what is the, what does this mathematical equation y is equals to mx, y is equals to x square represent? किसका equation होता है? This is an equation of a parabola, right? So parabola, so therefore at smaller values of c, at lower values of c, what happens? This term dominates. So what term dominates? At lower values of speed, when the value of c is small, c square dominates, and therefore the nature of the curve is decided by what? Parabolic shape. Therefore it has a parabolic shape. Now there is also a decrease in the the fraction of the molecules. Now this decrease, we can say that this is because of this exponential factor which is having a negative sign. Now we have c square here also, but with a negative sign, and we also know that if there is something which is decreasing or increasing, with the exponent the decrease or increase becomes more pronounced. So you decrease hoga, this is because of the exponential part, right? Now since this fraction is a product of the two quantities, right, it is a product of two terms, so therefore when these two, so it is going to have a maxima here. Where will it have a maxima? Where the product of the two terms is what? Maximum, right? So mathematically we can define this maxima as when the first derivative is equal to 0, we can define it that, but from this equation it is quite clear that the distribution which gaseous molecules follow is because of these two factors. Now let us understand, let us discuss about the physical significance of having higher velocities and having lower velocities, right? Now in a sample where we have many molecules, here we have defined the number, we have n number of molecules. So there are very few molecules which are moving with very low velocity, very few molecules which are having very high velocity, and most of the molecules are moving with this velocity, right? Here you see is this number. So this is from the y-axis, you see that this is the velocity which is possessed by what? Maximum number of the molecules. So it is also known as most probable velocity. So what is most probable velocity? The velocity which is possessed by most of the molecules which are present in the gaseous sample. Now we see that this particular equation is valid at a particular temperature. We need to define the temperature, so we get one curve. So this curve has been plotted at one particular temperature. So it becomes really important here to understand that what will happen if we try to study this kind of distribution at a different temperature. Will it remain same or will it be different? So let us understand the effect of temperature on this distribution curve in the next part of the lecture.
Hello everyone, I am Dr. Seema Thakran. Welcome to S. Chand Academy. I will be teaching you topics limit and continuity, differentiability, partial differentiation, tangents and normals, curvature, curve tracing and many more. Please like, share and subscribe S. Chand Academy and don't forget to press the bell icon for the future updates.
Welcome back to S. Chand Academy. Before the break, I had asked you a question that what will be the effect of temperature on this particular distribution? Will it remain same or will it be different? So let us now understand the effect of temperature on this distribution curve. So these curves I have plotted for one molecule. These have been plotted for nitrogen molecule at different temperatures. So what are those different temperatures? It has been plotted at 100 Kelvin, 200 Kelvin, 300 Kelvin and 400 Kelvin. Now these curves have been specifically plotted to see that if we increase or decrease the temperature, what effect will it have on the distribution of the molecular velocities, right? So now we know the relationship between the molecular velocities and the kinetic energies and temperature, and we know that when the temperature increases, what happens? At an elevated temperature, the molecules would also move with higher velocities. And since velocity is related to the kinetic energy, they are directly proportional. So that means the molecules will be having now higher velocities. So they would be moving with higher velocities. So what happens here is that if you see that this particular curve has been plotted at 100 Kelvin. Now we see that this is what is this value? This is your most probable velocity at 100 Kelvin. Now what happens to this most probable velocity at 200 Kelvin? The grey curve represents the most probable velocity at 200 Kelvin, right? Most probable velocity, you can see, since at higher temperature, more and more number of molecules would be moving with higher velocity. So therefore, the most probable velocity increases with increase in temperature. So that means the maxima in this curve shifts towards right hand side. In fact, we can easily see that this entire distribution curve only flattens towards right hand side. So what happens now, instead of having molecules having lower velocities at lower temperature, now most of the molecules will be having higher velocity. Also, the fraction of molecules, compare the fraction of molecules at if we see in this yellow curve, we see only this much portion. So only these many molecules are moving with higher velocity, very high velocity at 100 Kelvin. But if we compare it with the 200 Kelvin, and we see here that what fraction? This fraction has almost doubled. So this is the fraction of the molecules which are now moving with higher velocity. So earlier at 100 Kelvin only the molecules with having a small range, less number of molecules were moving with higher velocity. Now at higher temperature there are many molecules, and hence the fraction also increases. The fraction of molecules which possess higher velocity becomes higher. The rise in temperature therefore leads to an increase in the velocity of the molecules, kinetic energy of the molecules. So here at this point of time I would like to again go back to the expression which we have. So we can see here that temperature appears in this particular factor, it appears in the denominator. Also there is a negative sign, right? So we can see that this factor is known as Boltzmann factor. What it is known as? This is known as Boltzmann factor. So what happens to the Boltzmann factor at an elevated temperature? As the temperature increases, it is there in the denominator, so it is inversely proportional to the fraction, but there is a negative sign. So a double inverse will make it positive. So obviously the fraction of molecules, so fraction is proportional to Boltzmann factor. So the fraction of molecules having higher velocities at higher temperature will be higher because of this factor. So this Boltzmann factor in fact plays a very important role in many theories of the reaction kinetics as well. This factor was given by Boltzmann factor in order to understand the distribution of molecular velocities, kinetic energies and so on. So basically this tells us the effect of temperature upon the distribution of molecular velocity. So now after having understood the distribution of molecular velocities and the effect of temperature on the distribution, we can now convert that distribution function, or we can also have the Maxwell distribution in terms of energy. Since we know the relationship between kinetic energy and velocity, what is the relationship between kinetic energy and molecular velocity is E, which is kinetic energy, is given by half mc square, right? So this is the relation which relates the molecular velocity with kinetic energy, and therefore we can also write that C is equals to under root 2E by m, right? So what am I trying to explain you is that the same distribution curve which we wrote in terms of molecular velocities can also be written in terms of kinetic energy, right? The distribution is similar, but in what variable we are trying to study this distribution is different. Earlier we were discussing in terms of molecular velocities, now we are discussing in terms of molecular energies or kinetic energies. So what actually is changing here, that instead of having c square dc term which appeared in the earlier equation, we would be writing that term in terms of energy. So using this relationship between velocity and energy, and then further we can also differentiate this. So we can write c square equal to 2e by m. On differentiating this equation, we would be getting 2c dc, and then we would be getting here 2 de by m, right? So instead of c dc, so 2 and 2 can get cancelled, and in case we want to write c square dc, what we would be writing here, c de by m, and instead of c, what are we going to write, root 2e by m de by dm. So this is my c square dc. So what I do here, nothing very complicated. So what we have basically done is that we have now replaced this term c square dc with the term in terms of, we've rewritten it in terms of kinetic energy, and upon substituting the value of kinetic energy we would be getting an expression. This is the expression that we get, and the same expression, if we try to plot it, if we try to plot this particular distribution, we would be getting this kind of curve, which is similar to the Maxwell Boltzmann distribution for molecular velocity, with the exception that now the curve is no longer that symmetric, and that is quite obvious because the earlier we were having a factor of c square which was defining a perfect parabolic shape for this distribution curve, and now instead of that we would be having root e. So this is the energy distribution function. This has been plotted again for nitrogen gas at 100, 200 and 500 Kelvin. And not to mention again, here also the effect of temperature is similar, that upon increasing the temperature, more and more number of molecules would be moving with higher kinetic energies, and therefore the entire curve shifts towards right hand side. The application of Maxwell Boltzmann distribution of molecular velocities is to find out the various types of molecular velocities which have been defined for gaseous molecules. So let us now first understand the definitions of various types of velocities, and then we would correlate it to their location on the Maxwell distribution curve. So first of all, let us define most probable velocity. Partly I have already explained it to you. It is the velocity possessed by maximum number of molecules of a gas at a given temperature. Again, to mention, temperature is very important because temperature will change the nature of the curve, will change the nature of the distribution function, right? And then we would be defining the average velocity. Average is same as we've been doing in the statistics. It is the arithmetic mean of different velocities which are possessed by different molecules of a gas in a given sample. So we may define, or we may write the mathematical expression for average velocity as in it is defined by C average, which is given by C1. Let's say different molecules are having different velocities, C1, C2, C3, C4 and so on up to Cn, and this n is equal to what? Total number of molecules. So taking the average of all velocities, we define this velocity which is called average velocity, right? We may define it alternatively n1 c1 if we have, let's say, n1 number of molecules having c1 velocity, n2 number of molecules having c2 velocity and so on, say n molecules are having velocities Cn and taking their average again. So these are two different forms in which the velocities have been defined. So the average velocity can be defined this way, like and then next we would be defining the third type of velocity, which is your root mean square velocity. The root mean square, we call it CRMS. Just go one step one, mean square. Let's not concentrate first on root, let's concentrate on mean square. So we take the square of the velocities, right? So instead of taking C1, C2, now we would be taking C1 square, C2 square, C3 square and so on up to Cn square. Now we have taken their squares, we would be now taking their mean. How do we take their mean? Is by dividing them with total number of molecules and then taking their root. So square their mean and then root. Now taking the root of this, so this velocity becomes your root mean square velocity. So these are three different types of velocities which we define for gaseous molecules, and if we want to know their location or their position on the Maxwell Boltzmann distribution curve. So again we have drawn here the distribution curve. In the distribution curve, the most probable velocity is defined by the maxima of the curve. Maxima of this curve represents the most probable velocity. Then average is average. It comes in between RMS and average. We can define it and we can denote it by V also, we can denote it by C also. It depends on your convenience, right. So V average is the average velocity which comes in between, and the highest of all is root mean square velocities, right. So the three velocities are represented on this Maxwell Boltzmann distribution curves like this, and comparing their magnitude. So the derivation we are not going to do for these velocities. We can actually derive the velocity. Most probable is quite easy to derive. We can take the first derivative of the distribution curve and put it equal to 0. Solving this, we would be getting the expression for most probable velocity, which is equal to under root 2r by m. And then the average velocity again can be calculated, and the expression for the same is given by root 8 RT by m. Root mean square velocity also have been calculated, and the expression for the same is root 3 RT by m. So these three types of velocities which have been defined for gaseous molecules can be arranged. In the sense, we have already seen their position or location in the Maxwell Boltzmann distribution curve. Let us compare now the magnitude of these velocities. So comparing the magnitude of these velocities, we can see that comparing these two, so which of the three is highest in magnitude is root mean square, because we compare the RT by m factor is going to be same in all these expressions. What is changing is this particular constant value. So 3 of all the 3, 2, 8 by pi, 3 is biggest. So root mean square velocity, and then we would be having average velocity, and the least of all is your most probable velocities, and their ratios are expressed as this. Now coming down to the final, the most useful expression or relationship between the velocity and the temperature, because we have learned a lot about the molecular velocities, a lot about the kinetic energy, and time and again I had repeated the importance or significance of temperature. What role does it play in deciding the nature of distribution curves? So let us now understand the effect of temperature on molecular, or the quantitative relationship between the temperature and molecular velocities, or temperature and kinetic energies. So again go back to the the previous lecture where we had derived this kinetic gas equation. In this kinetic gas equation, if I multiply by 2 here, divide by 2 here, we would be getting this expression, and this is nothing but this is what the kinetic energy for 1 mole of a gas. So if this is so, then we can write it that PV is equal to 2 by 3, PV is equals to 2 by 3 E, where E is what? Your kinetic energy, right? So we can rewrite this for an ideal gas, PV is equals to RT. Therefore, we can get this expression that the total kinetic energy of a gaseous, 1 mole of a gas is given by 3/2 RT. And now we know the relationship between kinetic energy and velocity. Since kinetic energy is related to the velocity by the expression half mc square, therefore, here you can see that energy is directly proportional to temperature. So, kinetic energy is proportional to the power 1 of temperature, whereas molecular velocity or the velocity of a molecule is proportional to the square root of the temperature. To conclude, I would now like to tell you the effect. It means that for a particular molecule, see, the molecular velocity does not depend upon any other factor but only upon temperature. It does not even depend upon the size of the molecule. So, even if you take hydrogen molecule, nitrogen molecule, carbon dioxide molecule, and you try to compare their velocities. So, if the temperature is same, all these 3 gases are going to have the same velocity, which is indicated by this expression. So, to conclude here with that, in this particular lecture, we have tried to understand the molecular distribution of Maxwell Boltzmann distribution of molecular velocities and the effect of temperature on these molecular velocities and the distribution curve. So, if you want to read in details about the topic, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. Kindly like, share and subscribe, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.